Hello, howdy, I hope you are doing well. Today, to dig into some things about thinking and education, specifically physics. A lot of lessons and ideas here. I'm going to read, discuss, analyze, develop ideas out of an article entitled Teaching Heat, the Rise and Fall of the Caloric Theory, written by Dr. Michael Fowler, PhD in physics, retired, University of Virginia. And I'll put a link to it, of course. You can read along, look at it later, as you please. But a link will be in the show notes. And if you like it, geez, please, write him and tell him thanks. Good stuff, good work. People like this deserve our gratitude and thanks for doing good things. I think rewarding what is good is more important than punishing what is bad. We need more rewarding in our world. People are quick to jump on hating stuff. I mean, geez, you see it all over the place, kind of metaphorically speaking, in an exaggerated way all over today. We need more people jumping on gratitude and things like that for more things in everyday life. A lot of good things out there that aren't being appreciated as much as they should, encouraged, publicized, communicated, rewarded. So, we need to do some of that, please. Let's tell Michael Fowler thank you for this good article and other work he's done, which I'll put a link to. He's got some links on courses he's taught, has them for free for students, homeschoolers, and so on. I'll put some links to some things he's done, as I say. So, teaching heat. Now, he starts out, he says, quote, wait, first of all, let me arrange this. Okay, yeah, just get the click here, this breaker thing will go behind here. Make sure I got this thing set up. So, microphone working, correct microphone, so on and so forth. Okay, I think I'm good to go. So, quote, in my experience, there is much to be gained from teaching physics with some historical perspective. Unfortunately, the trend in physics textbooks these days is in the opposite direction. 30 years ago, most standard texts included some discussion of how and when basic concepts in physics developed. Recent editions of these same books, much heavier and more colorful, have dropped that material in favor of endless, detailed instruction on how to solve textbook problems. This may be, in part, unnecessary response to less well-prepared students and possibly teachers, but the new texts, despite four-color artwork on shiny paper, are rather dreary. My solution is simply to use the text as a source of problems and for backup reading, and to use a fair amount of historical material and demonstrations in class, and to post my class notes on the web. Homework assignments include calculations based on historical experiments. For example, estimate the mechanical equivalent of heat using Rumford's cannon boring data and Watt's estimate of 1 horsepower. Most of the students enjoy this approach, unquote. Yes. Very important to go over the historical development. Agreed. Now, there's a deep reason here. Physics, chemistry, it should be done. Because when you look at the essence of the historical development, when you do this right, you can see how things developed logically. You can flesh out what people needed to know to figure out some concepts, figure out science. Like experimentation doesn't just pop out of nowhere magically like everybody knows it. Nonsense. Even some PhDs in physics don't really have a proper understanding of experimentation, its nature, what it is for, its philosophy, its epistemology, its logic. They don't know what science is about. And that's a mistake some people make. Physicists study things in the world. They do not study thought. They are not scientists of science. They are scientists of material things, like of electricity or something. So unless some physicist functions as an epistemologist as well, they do not know what they're talking about very much in terms of how science works. They just know what they do and how they're trained. They don't have the bigger picture context to know. As you can tell, because a lot of them, there's a number, I should say, that have gifty ideas. They're influenced by Immanuel Kant, by Plato, by some like formalists and some other bad ideas. They've got philosophies that contradict what physics actually does. But some of that could be taken care of to be less common, I think, if people studied the history of things more, did more actual experiments instead of just doing a bunch of word problems, acting as if math is just physics is just a addendum to math. You just do a bunch of word problems. If people learn more history, they would have to delve more into reasoning, logic, see what Galileo had to do to develop his science, his two new sciences. This is one of his books is called. Good book. I recommend it. People read it. That could be read in part in high school too. Very good writing. It's accessible to people. But one thing he had to do was study logic and epistemology and correct mistakes many people made in their thinking processes when thinking they're doing science. People were influenced by Plato. Ptolemy had some bad ideas from that. They didn't have a proper understanding of the role of the evidence of the senses and experience. They didn't have a proper understanding of how concepts come out of experience and are connected to them integrally. So people would learn things like that. There would be less mistakes. People would understand science better, people and scientists. Scientists would have a better understanding of what they're actually doing. People would be more interested in in teaching it and learning it because they would be involved in the world and how it works and cause-effect relationships instead of just doing a bunch of math problems. So it would help in a variety of ways. Studying physics historically, you get to see how things developed, how inductions, generalizations occurred, how people were able to figure out the nature of things. How did people figure out what electricity was? What are some of the step-by-step processes? How did they go from the evidence of the senses and basic things to figuring out that there are charges? And where did this plus and minus come from? And electric current and like batteries. How did people develop that? Because that's what we need to know to do things on our own. In everyday life, we got to start with the basics and the given and not much knowledge a lot of times and work out ideas from there. Develop sequences of thought, identifying sequences of causation to get things done in life. And we ain't going to learn that by doing a bunch of word problems because that doesn't happen very often. We need some of that. We got to do a lot of math, kind of manipulate mathematical equations to look at the cause-effect relationships in physics and chemistry and finance and everything. But that's irrelevant and useless and a waste if we don't understand reality and cause-effect relationships and the nature of things and how science really works and how thinking really works. So studying this is important. It's essential for really learning how we think and reason and how science actually works. We need to learn to distinguish more between the scientific method and the scientific community because they're not the same at all. And that's a mistake I see nowadays. I don't care if someone's a scientist, so-called, doesn't mean they know actual science. When you study human history, that's a lot clearer. I'll put a link to some mistakes in science and how some so-called scientists rejected valid conclusions. Or when Ohm discovered Ohm's laws, one reason he was rejected was because, I'll put a quote. Some people said he was, and they looked down on him with contempt and disregarded what he said because he used experimentation and they used pure reason. If you don't get it by pure reason, you're not a real scientist, which is ludicrous. That's anti-Galileo. That's anti-Newton. That's not what Galileo and Newton did. Galileo and Newton immersed themselves in experience to learn and do science. They didn't separate themselves and be Platonic. The Germans were being Platonic, which is inexcusable in that time after Galileo and Newton and others. Plato's day, there's a little more excuse, but not after Newton. So, many reasons to study things historically. So, and then we learn the importance of philosophy, philosophic fundamentals, getting things correct in metaphysics and epistemology. Metaphysics, the nature of the world. Can we know it? Are there cause-effect relationships? Is everything chance? Can we not know the world, as Kant says? Immanuel Kant? Or can we know it, as Aristotle says? Epistemology, it's like the science of, part of philosophy that studies understanding. Logic is a part of it. Epistemology is broader. In epistemology, we identify that the evidence of the senses are basic. As Galileo said about Aristotle, all human reasoning must be placed second to direct experience. That's an epistemological principle. Whereas Plato would say, all experience must be placed second to human making stuff up, imagination, so-called what he would call reason. So philosophic ideas are important there too. We need to see, as I say, to repeat, how things develop step by step from the evidence of the senses, how we build ideas and theories up. That is an important thing to learn for knowing fully and more completely what a human is and how to be human and live a good life. That helps us. It's something we should do. We'd all be better off than we are now. As much as we might be enjoying our lives and stuff, we could all improve. There are always unknowns. We all have our weaknesses, things to improve. This is one thing that would help. We have strengths, we have weaknesses. We have strengths, we're doing some good things in life. We got pleasure, we got some happiness. But we can do more. We should strive and work hard to help children and students do even better, be the best they can be. That's just kind of a responsibility of being an adult and a parent and a teacher. So we'd help with that. People would learn better how we actually think and learn and know and understand. If it's taught historically, because we would go through that process many, many times with scientists and different discoveries. And that's one thing. And then we'd learn, as I say, the importance of some philosophic fundamentals. What is truth is a philosophic question. It is not a scientific question. Science can't even get off the ground until people can figure out what the truth is. Until then, forget it. So there's a little development of why the historical perspective is important. Okay. Quote, I strongly believe that it is not a waste of time to discuss some earlier theories that turned out to be wrong. In fact, these earlier theories are often close to the student's current thinking. Unquote. Yeah, because students are learning something, they don't know everything, they are wrong on some things, or maybe they have read something and memorized something and know some words and think they understand something which they don't. They don't know it. They don't have examples. They're just going with words. They haven't learned what knowledge really is yet, because that's what it is to be a student. I mean, you don't know. Some people never get out of that, and they call themselves nominalists when they get older. They've never learned, even though they're in their 30s or 50s or 70s, they've never really learned what knowledge is. So there are a variety of reasons that will cause students to be wrong about things. And so studying these ideas can help them challenge the students, help them see that great minds are also wrong. It's just part of being human. And then we can be a little bit more understanding of other people at the difficulty of knowing some things. So important reasons there. Okay, so again, quote, I strongly believe that it is not a waste of time to discuss some earlier theories that turned out to be wrong. In fact, these earlier theories are often close to the students' current thinking, so challenging them as to why those ideas were finally abandoned can stir the critical faculties and lead to better understanding. A case in point is the caloric theory of heat. Unquote. Okay, so the caloric theory was a theory about heat way back 1700s. Not the current theory, so this is wrong. So at this time, with the caloric theory, people thought everything was a stuff. They thought heat would be like an imponderable, meaning not having weight. There was a stuff that didn't have a weight. You'd put it on a scale, and there could be more heat in something or less, but this stuff, this heat stuff, like water, like some kind of fluid maybe, wouldn't actually give it weight. You couldn't weigh it. It was imponderable. IM meaning not, ponder like for weight. And some people thought, what was it? I had that in my head. There's some other thing like what? I think electricity. They might have thought was an imponderable as well. Some kind of stuff that couldn't be weighed. There are some other things like that. So that's kind of the caloric theory of heat. I can read a little bit more about it later. But it was a stuff, and let me see if I can find in this one book really quickly some stuff about now Cleghorn. I guess it's in a different part of the book. So never mind for right now. Okay, caloric theory of heat. Okay, so quote, of course, the students are vaguely aware that it's not right, but their intuitive ideas of heat, based on everyday experience, have probably led them to construct an operational model not too different from the caloric one. So we go ahead and discuss heat from this naive point of view and mention the first recorded systematic experiments on heat and heat flow. For example, Ben Franklin measured heat flow down rods of different materials by seeing how long it took to melt wax, and thereby compared the thermal conductivities of different metals, a matter of real practical importance in designing stoves, for example. Franklin believed some weightless, or almost weightless, caloric fluid was flowing down these rods. Recall he thought the same thing about electricity. There was some electric fluid flowing when an object was being charged electrically. And there he was absolutely correct. Like the electric fluid, Franklin believed the caloric fluid would flow from one object to another, but overall, there was always the same amount of fluid. It was conserved. And that's basic caloric theory. And that's, unquote, and that's one of the premises of the caloric theory thing, that it's conserved. Or maybe I can find those things, that some principles Cleghorn, the scientist, said about the caloric theory. But again, not seeing it. I don't remember where that was. So I guess So, to repeat, I shall try to find that later and read it. So, quote, we next discuss Joseph Black's ideas and careful experiments on heat, how it always flows from hot to cold things and evens out in a room with no heat source after a time. I should mention that the evolution of thermometers up to Fahrenheit was covered immediately before this review of caloric theory, unquote. So in other words, in class he had talked about Fahrenheit. He had talked about how people went from some work Galileo did to Fahrenheit to Celsius, maybe not Celsius, but up to Fahrenheit. But he had discussed thermometers before going over caloric theory. Quote, at this point, the quantitative concept of heat capacity is introduced, deviating only slightly from historical correctness by using Celsius and grams from the start. We perform one of Black's experiments in the lecture, using a calorimeter to find the specific heat of a piece of metal. The students are asked to discuss and predict it first. Almost all of them expect the specific heat of copper to be greater than that for water, so the opposite result gets their attention. This naturally leads to a presentation of a wider range of results, and the mysterious findings of Dulong and Petit that the heat capacity per atom seems to be a constant, no matter what the weight of the atoms, unquote. Sweet. So, Black, Joseph Black. So he was a physicist that did some early work in the study of heat. And let me see, I can read in one textbook some stuff he says. This is from Introductory Physics by Dr. Herbert Priestley, a chapter called The Nature of Heat, page 135. He says, in talking about Joseph Black, who was 1728 to 1799, and professor of medicine and chemistry at the University of Glasgow in Edinburgh, in England. So move this little marker here. Okay, so he began to investigate. So this is quote. He began to investigate the general belief that the amount of heat required to raise the temperature of any body by a given amount was proportional to the chemistry of the body. Fahrenheit, by mixing together water and mercury at different temperatures, had found that despite its much greater density, the heating and cooling effect of a given volume of mercury was only 2/3 that of the same volume of water. From these results, Black concluded that, quote, the quantities of heat which different kinds of matter must receive to reduce them to equilibrium with one another, or to raise their temperature by an equal number of degrees, are not in proportion to the quantity of matter in each, but in proportion widely different from this. I lost my place. There we go. So Fahrenheit's experiments led Black to compare the heating and cooling effects of other substances with corresponding effects of an equal bulk of water, obtaining by the different substances values he called their capacities for heat. So the heat capacity thing comes from black. How much heat can they hold? Kind of like how much stuff can be like sucked up by it, metaphorically speaking. And he came up with the idea of latent heat. Latent being hidden. Hidden heat. So quoting again. Oh, and to be clear, I said obtaining for the different substances values he called their capacities for heat, unquote. I forgot to say my unquote. So this is interesting. So quote, and then I'll be quoting within here with what Black says. So I'll be quoting Priestley, and the second quote will be what Black says. So quote, Black arrived at his best known discovery, that of latent heat, through study of the problem of melting. In his time, quote, fluidity was universally considered as produced by a small addition to the quantity of heat which a body contains. When it is once heated up to its melting point, and the return of the body to the solid state, as depending on a very small diminution of the quantity of heat, after it is cooled to that same degree, unquote. He, quote, soon found reason to object, unquote, to this universal opinion, quote, as inconsistent with many remarkable facts when attentively considered, and I endeavored to show that these facts are convincing proofs that fluidity is produced by heat in a very different manner. Black agreed that if the large masses of snow and ice accumulating in severe weather were suddenly and completely to convert to water as soon as atmospheric temperatures reached the melting point, the result would be torrents that would, quote, tear up and sweep away everything, and that so suddenly that mankind would have great difficulty to escape, unquote, unquote. Interesting, right? So there's latent heat, there's hidden heat. It takes heat to change the state of something. And this is a simple example. So history helped so much, bringing this example up from Joseph Black, showing how they were making basic observations that led to deeper results. Science comes from the evidence of the senses, from integrating and connecting, from cognitive integration. Integration being connect something into a whole. Like that's what theories do. That's what concepts do. That's what philosophy does. But there's snow, and as things heat up in the atmosphere, the heat goes into changing from ice to water, and then to warming up the water. And it's got to warm up the snow also. But if, as some people thought, if things went from ice to water immediately at 32 suddenly, as Black points out, there'd be deluges all over the place. It's like a theory that's not consistent with reality. Therefore, it's the theory that's got to be thrown out, not the experience. So some Platonists would throw out the experience and just say that you don't know what you're talking about. My ideas are perfect. That's a Platonic idea of science, so-called science. But as Galileo pointed out, quote, all human reasoning must be placed second to direct experience, unquote. So that's what Black's doing here. So there's a little bit about Joseph Black, what he did, who he was, getting heat capacities. Now, It helps you see why it's important to study Black. And there's more people could learn about him, his experiments and everything. And then, of course, Dulong Petit, more advanced work. They looked at some metals and found out that the amount of heat that a metal would absorb would be approximately the same per atom. Okay, maybe if I remember, I'll put a link to that in the show description as well. So, quote, once we start thinking about atoms, it becomes clear that some kind of microscopic picture of the caloric fluid flow must be constructed. Okay, it wasn't clear to everyone at the time. Even almost a century later, some eminent German scientists, such as Ostwald and Mach, were arguing against atomic models, unquote. So yeah, I think heat was one thing that helped prove the atomic theory because it's a theory. It has to explain different things. That's what theories do. So learning this would help people learn about theories and when the atomic theory was actually proven. What is the atomic theory? What does it mean to prove a theory? The theory of universal gravitation, the theory of heat, the theory of atoms, the atomic theory, the atomic theory that everything's made, all material stuff is made of atoms. But if that's the case, then the atomic theory would have to explain chemical reactions. It would have to explain electricity. It would have to explain heat. And hence, what Petit and Dulong did was important in establishing the atomic theory. And it took a while for it to be established. It wasn't until late 1800s, early 1900s, I think, that it was finally proven comprehensively and properly. Okay. Quote, they felt the business of science was the discovery. So I'll start over. Okay, quote, once we start thinking about atoms, it becomes clear that some kind of microscopic picture of the caloric fluid flow must be constructed. Okay, it wasn't clear to everyone at the time. Even almost a century later, some eminent German scientists, such as Ostwald and Mach, were arguing against atomic models. They felt the business of science was the discovery of laws relating observable quantities, such as pressure, volume, and temperature of a gas, and attempts to interpret these laws in terms of unobservable entities such as atoms were unverifiable fantasies, unquote. So they have some bad philosophy. Mach, Oswald, horrible philosophically. Very bad philosophies. So they were saying that all we could do is describe what we could see. They had a bad view of reasoning, concept, formation, things like that. So, quote, time has shown how they were wrong. Now only string theorists have to endure that kind of criticism. Anyway, back to the subject. Our students certainly agree that some microscopic theory is needed. So how do we begin to construct one? We know that heat expands gas. In class, we'd recently discussed Galileo's thermometer. How does the caloric theory explain that? Newton imagined atoms in a gas rather like soft oranges in a crate, taking up most of the room available, and coated with this caloric fluid, so that on pouring in more caloric, the atoms swelled in size. The atoms in a solid or liquid had a lot less caloric. That's why it took so much heat, pumping in caloric, to boil water. That sounds reasonable, but the caloric theory did much more. The whole theory of heat flow in solids, including important problems like the cooling of the Earth over geological time, were analyzed quantitatively using sophisticated mathematical techniques developed in France by Fourier and others, applied to the caloric theory, and these methods and results are still good. Furthermore, as we shall see shortly, Carnot developed a theory of the steam engine based on caloric theory, which was largely correct and shed new light on some of the most pressing technological problems of the era, unquote. So it did have some green light. They were looking at flow heat does kind of flow. So there were some red light things about this and some green light. If it was totally okay, then it would have been proven valid and it would have been able to explain atoms, would have been consistent with atoms, the caloric theory, but it's not. And so you got to see what the green light things are in it and what the failures are and correct things. So, invalid idea theory overall that, again, you got to get these bad ideas, throw them all out, keep the good ideas in it, get rid of the whole theory, but get the good ideas into a new theory. So, quote, but a caloric theory has to explain other things. For example, why does friction cause heating? The standard argument was that the stress of rubbing surfaces together forced some caloric fluid to be pushed out from between the atoms, and it appeared as heat. This was the real weak point of the theory, and this is where Rumford attacked. In manufacturing cannons for the Bavarian military, Rumford found the necessary grinding to hollow out the barrel produced huge amounts of frictional heat, which continued to flow as long as the grinding was maintained. This apparently endless supply of caloric posed a big problem. Why should an ordinary piece of metal contain an apparently infinite amount of caloric fluid? Rumford decided a better explanation was that the friction of grinding caused some kind of internal invisible microscopic motion in the metal, and the flowing out of heat was nothing but this motion being communicated, the jiggling atoms causing neighboring atoms to jiggle as they came into contact. The caloric fluid flow was perhaps just a useful large-scale picture of the microscopic motion spreading through the material. If Rumford's picture was correct, the fluid was mechanically created by the friction and, unlike electricity, was not a conserved quantity, unquote. So, Rumford, one thing he did was get, I forget the exact thing, 18 pounds of water maybe. So he got this thing set up, water in a wooden container, so it's kind of insulated from the surroundings. A piece of brass, I think, was put in it. I forgot how much it weighed. Was that maybe 18 pounds? 2 gallons of water or something or other. I'll put the detail in the show description. But then he got a steel borer to bore out the brass to make a cannon. And he started that working, and the cannon was in water. And over a period of several hours, the water went from, I don't know, maybe 50 degrees to 212. It heated up and kept boiling off. So there's not, so the caloric theory had to be wrong because there is not an infinite amount of stuff that could be squeezed out of the cannon. There's a limited amount. And remember, the stuff is thermally insulated. So it can't just be coming in from somewhere else. So it's the heat, the motion, the friction that is causing the heat. And I'll see. Well, yeah, I don't think I can find that quickly right now to read it, but that's an experiment that was done. So that's what Rumford did. And again, that's something real that students can wrap their minds around, grasp how that could happen. And then you could dig into these other experiments that come later. But, quote, but Rumford's work, published in 1798, did not kill the caloric theory. After all, the caloric theory had explained a lot. Rumford's critics suggested that maybe somehow the fragments of metal shaved off had lost all their caloric. He had tried to check for that, but his method was not completely convincing. To appreciate the next major advance in understanding heat, the backdrop of the developing industrial economy must be borne in mind. The first modern factories were textile mills with many power looms driven by a large water wheel, so the water falling under gravity was a source of power. By the early 1800s, the water wheels were being replaced by steam engines. The first attempt to construct a theory of the steam engine was by Sadi Carnot in the 1820s. His idea was that just as water flows downhill, caloric flows from hot to cold. And the steam engine utilizes this caloric flow just as a water wheel takes energy from falling water. His analysis led to many correct conclusions, such as that the amount of work that a given amount of heat would provide depended on the height of the temperature drop. And there was a limit to how much work could be extracted. Carnot proved that the limit was the work provided by a reversible engine, one with no friction and heat exchange only between objects at the same temperature. We go over an analysis of why you can't do better than a reversible engine in class. These results, drawn from an analysis of a flawed theory, nevertheless are central to our present understanding of steam engines and internal combustion engines. Sad to report, Carnot died at a young age, and his work was almost unknown until the 1850s, unquote. So, so he developed a theory of some kind of reversible engine, whereas some, you can't reverse them because, once something goes into heat, you can't pull the energy back. It's become kind of friction, and hence you get the idea of like entropy and disorder. So that's some of the theory he did. Help really understand these things and see what we could build and what we couldn't. Okay. Quote, another scientist to be fascinated with water wheels in the 1820s was Julius Robert Meyer, born in the mill town of Heilbronn, Germany, on the river Neckar in 1814. The town's whole economy was based on water power. The 10-year-old Meyer had a great idea. Why not use part of a water wheel's output to drive an Archimedean screw, which would pump the water back up again? That way, you wouldn't have to rely on the river at all. He decided to build a model. His first try didn't quite work. Some water was pumped back up, but not enough. But surely that could be taken care of by putting in a gear train to make the screw run faster? Disappointingly, he found the water wheel had a tougher time turning the screw faster, and he needed to supply more water over the wheel, putting him back to square one. Increasingly ingenious but unsuccessful fixes finally convinced him that in fact there was no solution. There was no way to arrange a machine to do work for nothing. This lesson stayed with him for life, unquote. Right. The machine can't do work for nothing. You can't get... that can be a... that misunderstanding is with us today. Some people think that there's sometimes you can hear about people thinking they've invented some machine that works forever. I forgot what it's called right now. Must need more coffee or something. Okay. But, quote, Meyer studied to become a medical doctor. His studies included one physics course. And in 1840, at age 25, he signed on as a ship's doctor on the Java, bounded for the tropics. Shortly after reaching the Dutch East Indies, some of the sailors became ill, and Meyer's treatment included bloodletting. He was amazed to find that the venous blood was a bright red, almost the same as arterial blood. Back in Germany, the venous blood was much darker, and there was a reason. The chemist Lavoisier had explained that the body's use of food, at least in part, amounted to burning it in a controlled way to supply warmth. The dark venous blood, in effect, contained the ashes to be delivered to the lungs and expelled as carbon dioxide. Meyer concluded that less burning of food was needed to keep warm in the tropics, hence the less dark blood, unquote. So, yeah, like Faraday, the great physicist Faraday did some lectures about that, some Christmas lectures, the chemical history of a candle, in which he talked about the relationship between the chemical similarity between a burning candle and breathing in lungs, the like kind of combustion that goes on in our lungs. So about Meyer. So here's a bit about him. So here's another quote from Introductory Physics by Dr. Herbert Priestley. The relation of Joule, 1818, 1889. Whoops, Joule. Okay, wrong place. Sorry. Where's Meyer? Here's Meyer on this other page over here. I was on the wrong page. So, right. While bleeding patients on the voyage, and the ship was named Java in the tropics. So, I won't repeat this part. But, so here to continue with what Dr. Fowler said, quote, this seemed to support the view that the heat of the body came from chemical energy in consumed food. Meyer assumed that the mechanical energy of the muscles came from the same source, leading in turn to the conclusion that heat and mechanical and chemical energy are equivalent and interconvertible. The first paper, which reported the above facts and theory, concluded with a calculation of the mechanical equivalent of heat, 3.58 joules per calorie, on the basis of temperature change and mechanical work done in the case of expansion of a gas. The second and third papers, unquote, the papers that Meyer published, of course, okay, quote, the second and third papers extended these ideas on virtually a universe scale. Mechanical work, chemical action, heat, light, electricity, and magnetism are all forms of force, energy, and a constant total in the universe, making the conservation principle a universal law. The ultimate origin of nearly all heat and mechanical power is to be found in the sun. Meyer answered the questions. What is heat? Quote, Meyer answered the question, what is heat, by saying that heat was a form of energy which could be transformed into mechanical effect. He recognized how the steam engine transforms heat into work, and that heat may be produced when work is done, as when a moving body is slowed down or brought to rest by friction. In such a case, there was not a loss of energy, as had been believed up to that time. The energy supposedly lost actually was transformed into heat. The production of heat by an electric current is at the expense of chemical energy used up in the electric cell, supplying the current, and the energy stored in electrically charged bodies can only come from the work done in placing the charge on the body. Meyer gave 25 examples of energy transformations and an extensive discussion of energy relationships in nature, such as in muscular work, where the chemical energy of food is transformed directly into mechanical energy, potential or kinetic. Without facilities for elaborate experimentation, money of spare time, and with a limited knowledge of physics, Meyer showed some of the marks of genius. His life was a tragic one by virtue of that genius. He was so far ahead of his time that he was ignored by the great and ridiculed by the less great, and recognition of his work was delayed. He attempted suicide and for a time became mentally deranged. He recovered and lived to receive a considerable measure of the honor that was his due, unquote. Yeah, so it sounds like some people were total jerks to him. Poor guy. Was treated like a jerk. I should say some people were jerks to him, and hence he suffered socially, psychologically. Unfortunate, because he was scientifically better than them, connected to reality, drawing conclusions from the world. So that's some of the work he did. Very important, should have been recognized. But since people are influenced by Plato, they have some bad ideas of what reasoning is and logic. There's a fail. So here's another instance of the importance of studying things historically. So we learn how to see what science really is versus what the scientific community is. When does someone have good reasoning skills and when they don't? That should be something we learn so we can use to distinguish people as well. What kind of boss is rational and good and is going to help, is good at their job and good at teaching versus who is not so good and has bad thinking skills or bad philosophy. Very important. So, quote, back to Dr. Michael Fowler's article. Now that we read a little bit about Meyer in Introductory Physics by Herbert Priestley. So, Dr. Michael Fowler again. Quote, now, Lavoisier had claimed that the amount of heat generated by burning or oxygenation of a certain amount of carbon didn't depend on the sequence of chemical reactions involved. So the heat generated by blood chemistry, oxygenation, would be the same as that from uncontrolled, old-fashioned burning in air. This quantitative formulation led Meyer to think about how he would measure the heat generated in the body to equate it to the food burned. But this soon led to a problem. Anyone can generate extra heat just by rubbing the hands together. Or, for example, by turning a rusty, unoiled wheel. The axle will get hot. Does this outside heat also count as generated by the food? Presumably, yes. The food powers the body, and the body generates the heat, even if indirectly. Meyer was convinced from his childhood experience with the water wheel that nothing came from nothing, that outside heat couldn't just appear from nowhere. It had to have a cause. But he saw that if the indirectly generated heat must also be included, there's a problem. His analysis ran something like this. Suppose two people are each steadily turning large wheels at the same rate, and the wheels are equally hard to turn. One of them is our rusty, unoiled wheel from the last paragraph, and all that person's efforts are going into generating heat. But the other wheel has a smooth, oiled axle and generates a negligible amount of heat. It's equally hard to turn, though, because it's raising a large bucket of water from a deep well. How do we balance the food equals heat budget in the second case? Meyer was forced to the conclusion that for the food equals heat equation to make sense, there had to be another equivalence. A certain amount of mechanical work, measured, for example, by raising a known weight through a given distance, had to count the same as a certain amount of heat, measured by raising the temperature of a fixed amount of water, say a number of degrees. Unquote. So, you get some mechanical work. How would you measure that? How much work is there? You measure it by raising a weight through a given distance. A given weight through a given distance. Then you can tell how much work there is. You got a standard to compare different works. You get a weight. Can you lift it more or less? More or less work. So we know about the work, we can measure it. And then how do you measure the heat? By changing the temperature of a fixed amount of water. So we do these things. Then we can get this equivalence. So, quote, in modern terms, a joule has to be equivalent to a fixed number of calories, unquote. So calories like how much we eat. That's a heat thing. Quote, Joule was the first, or quote, Meyer was the first to spell out this mechanical equivalent of heat. And in 1842, he calculated the number using results of experiments done earlier in France on the specific heat of gases. French experimenters had measured the specific heat of the same gas at a constant pressure and at constant volume and constant pressure. Unquote. Sorry, there's a typo in here. C sub P, constant volume. C sub P, constant pressure. C sub V, constant volume. But it says constant pressure before C sub V. So, typo. We all make mistakes. So, quote, French experimenters had measured the specific heat of the same gas at constant volume and at constant pressure. They always found constant pressure measurements to be greater than constant volume measurements. The way to understand this is as follows. Consider two identical vertical cylinders, closed at the top by movable pistons. The pistons resting on the gas pressure, each enclosing the same amount of the same gas at the same temperature. Now supply heat to the two gases. For one gas, keep the piston fixed. For the other, allow it to rise. Now measure how much heat is needed to raise the gas temperature by 10 degrees, say. It is found that extra heat is needed for the gas at constant pressure, the one where the piston was allowed to rise. Unquote. So we got two identical containers, two cylinders. We can picture that. And we got like a piston at the top that can move up and down. Of course, a piston can move up and down. So you got these containers, like soft drink cans, got some gas in them, but instead of the top on the can, you got a piston that can move up or down, some circular thing inside the cylinder, and you heat up the gases. One, the piston cannot move, the other can go up. Then, you got to raise the temperature of the gas and push the piston up, so it'll take more work, more energy. So the one that is at constant pressure, but the volume can change, needs extra heat, extra work, extra energy. So, quote, Meyer asserted this was because, in that case, some of the heat had been expended as work to raise the piston. This followed very naturally from his previous thinking, and the French measurements led to a numerical value for the equivalence. Meyer understood the sequence. A chemical reaction produces heat and work. That work can then produce a definite amount of heat. This amounted to a statement of the conservation of energy. Sad to report, Meyer was not part of the German scientific establishment, and this groundbreaking work was ignored for some years. Meanwhile, in Manchester, England, the center of the Industrial Revolution, the same problem was being approached from a quite different direction by James Joule, the son of a prosperous brewer. Joule was lucky in that as a teenager, he was tutored at home along with his brother, John Dalton, the chemist who founded the atomic theory. Manchester was at the cutting edge of technological progress, and one exciting idea in the 1830s was that perhaps coal-driven steam engines could be replaced by battery-driven electric motors. Joule, in his 20s, set himself the task of improving the electric motor to the point where it could be competitive with the steam engine. But it was not to be. After years of effort, he concluded that at best it would take 5 pounds of zinc consumed in a battery to deliver the work from 1 pound of coal. But he learned a lot. He found an electric current in a wire produced heat at a rate I squared R, now known as Joule heating. The caloric theory interpretation was that caloric fluid originally in the battery was released along with the electric current and settled in the wire. However, Joule discovered the same heating took place with the current generated by moving the wire past a permanent magnet. It was difficult to see how the caloric fluid got into the wire in that situation. Ha! Excellent. Joule decided the caloric theory was suspect. He generated a current by applying a measured force to a dynamo and established that the heat appearing in the wire was always directly proportional to the work done by the force driving the dynamo. Finally, it dawned on him that the electrical intermediary was unnecessary. The heat could be produced directly by the force. If instead of turning a dynamo, it turned a paddle wheel turning water in an insulated can. It turned paddle wheels turning water in an insulated can. In this way, he found the mechanical equivalent of heat, the same number Mayer deduced from the French gas experiments. A few more paragraphs. Okay, that's unquote. A few more paragraphs. So cool. Quote, Joule's initial reception by the scientific establishment was not too different from Mayer's. He, too, was a provincial with a strange accent. Unquote. So he was ignored. And in Introductory Physics by Dr. Herbert Priestley, he says, it is perhaps of interest to note. So, quote, so Priestley is saying, who wrote the book, the author says, quote, it is perhaps of interest to note Lord Kelvin's comments on Joule's work. Quote, his boldness in making such large conclusions from such very small observational effects, unquote. And now a comment of Priestley, a parenthetical, quote, referring to the small temperature rise in the paddle wheel experiments, unquote, unquote from Priestley. And now back to Lord Kelvin, quote, the small effect is almost as noteworthy and admirable as a skill in extorting accuracy from them. So I'll read that again just in case the break made kind of cut it off. But and I guess some background. So Joule, basically, he had about a half degree Celsius temperature change that he was drawing his conclusions on. And some people didn't think that was much. They didn't grasp the significance and validity of his experimentation and reasoning. But Lord Kelvin is backing it up. So again, I'll say, quote, it is perhaps of interest to note Lord Kelvin's comments on Joule's work. Quote, his boldness in making such large conclusions from such very small observational effects is almost as noteworthy and admirable as his skill in extorting accuracy from them. I remember distinctly at the Royal Society, I think it was Graham or Miller saying simply, he did not believe Joule because he had nothing but hundredths of a degree to prove his case by, unquote, unquote. So, again, science versus the scientific community. We need to distinguish them. So now back to Dr. Fowler's article. Quote, I'll start again this paragraph. Quote, Joule's initial reception by the scientific establishment was not too different from Mayer's. He, too, was a provincial with a strange accent. But he had a lucky break in 1847 when he reported his work to a meeting of the British Association and William Thomson was in the audience. Thomson had just spent a year in Paris. He was fully familiar with Carnot's work and believed the caloric theory to be correct. But he knew that if Joule really had produced heat by stirring water, the caloric theory must be wrong. He said there were insuperable difficulties in reconciling the two. In fact, by this time, although many still believed in the caloric theory, it had run into other difficulties. Before the 1820s, almost everyone believed, following Newton, that light was a stream of particles. Around 1800, Herschel discovered that on passing sunlight through a prism and detecting the heat corresponding to the different colors, in fact, there was heat transmitted beyond the red. This suggested that radiant heat was caloric particles streaming through space, and no doubt very similar in character to light. But in the 1820s, it was unambiguously established that light was really a wave. Did this mean that heat was a wave too? Perhaps the caloric fluid was oscillations in the ether. Things were now very confused. In 1841, Joule wrote diplomatically, quote, "Let the space between these compound atoms be supposed to be filled with caloric ether in a state of vibration, or otherwise to be occupied with the oscillations of the atoms themselves," unquote. It transpired, though, that the difficulties in reconciling Carnot's theory and Joule's experiments were not as insuperable as Thomas had claimed. In 1850, a German professor, Rudolf Clausius, pointed out that Carnot's theory was still almost right. The only adjustment needed was that there was a little less heat emerging from the bottom of the caloric water wheel than went in at the top. Some of the heat became mechanical energy, the work the steam engine was performing. For real steam engines, the efficiency, the fraction of ingoing heat delivered as useful work, was so low that it was easy to understand why Carnot's picture had been accepted for so long. For the first time, with Clausius' paper, a coherent theory of heat emerged, and the days of the caloric theory drew to a close, unquote. So, good stuff. It's worth reading and rereading the article to assimilate, to look at details of it, put it back into the big picture, dig into more of what Dr. Michael Fowler here is saying in the historical record, in the scientific record, seeing what they did, so we can learn better how to think and reason. It's not just doing science. Science is about knowing cause-effect relationships, and that's something we all need to know. That's something we all care about in the world. How do we get one thing? How do we get another? What are the cause-effect things we do? And science helps us be rigorous and true and accurate about that. How do we get more money? How do we work smarter, not harder? How do we improve ourselves? How do we live a better life? How can we eat better? How can we take care of our yard better? What's the context? What are the cause-effect relationships? A yard, how many people stop and connect that to biology and to ecology? Not enough. We should do that more. Instead of just looking at a yard in isolation to everything else, or just like people put fertilizer on it thinking it's going to stay there, not grasping how things all interact and how a lot of the fertilizer is a waste and just washes into the water and goes elsewhere. It's a waste of money, pollutes water, things like that. We need to be learning things like this on this kind of level so we can understand things like fertilizer better, how to really take care of our lawn and eat well and live a good life, instead of just doing a bunch of word problems, which you do in isolation. It doesn't help you learn to really think and connect, whereas this stuff does. So I shall put a link to this, as I say. You can read it. I'll put a link to some other stuff. I'll talk about some of these books in the future. Introductory Physics by Dr. Herbert Priestley. I'll put a link to it. Good book. What he says about science is a bunch of nonsense. As I say, he's a physicist. He is not a scientist of science. He's not an epistemologist. He's not a logician. So he's wrong about what he says about science. He can do science, and he knows some scientific methods he's learned, but He's influenced by some bad philosophers and people like that. But it's a good book if you just pay attention to the science and really are able to think about how things develop inductively, how we generalize, how we put evidence together. That's an important thing to learn here. How do we form concepts of heat and figure out what heat is and what electricity is? How do we generalize about it and see what heat does and what electricity does? How do we form theories? If you really dig into the detail and see what's going on, you'll get a lot more out of it. And then there's one section of a book called Physics for the Inquiring Mind by Dr. Eric Rogers, a professor of physics, at Princeton, I think. He wrote, so Priestley wrote his book in the 50s. Eric Rogers wrote his book in the 70s, if I remember right. I don't like most of the book. The Inquiring Mind book, Physics for the Inquiring Mind, has a good section about astronomy. Very interesting. How astronomy developed. It goes way back to the beginnings and develops things step by step to after Newton. Again, we can learn a lot about how people form concepts. What is a planet? What does a planet do? What are the cause-effect relationships? Why do planets move as they do? What causes their motion? Excellent. Very good resource. But again, what Roger says about science is bunk and nonsense. He does not know philosophically how it works. If Fowler, no, not Fowler, sorry, Dr. Fowler. But if Priestley wrote the book, Priestley and Rogers, if they did physics the way they talked about how science is done, they'd be laughed out of the field. Because they are not researching, they're not looking at the history or the source of some ideas they think they believe about how physics is done. They're not seeing if they actually do it that way. They're not introspecting and identifying what is a concept? How do we form a concept? What is a generalization? How do we form generalizations? How do concepts relate to generalizations? How do generalizations relate to theories? What is a theory? What is an explanation? How do they relate? How do they relate to the evidence of the senses and to cause and effect? They did none of that. What does Immanuel Kant say? What does Plato say? What does Aristotle say? Some of these modern people that are so famous, that are so wrong, like Popper and Kuhn, where do they come from? What are their influences? Are they really right or are they wrong? And why? Science is about asking why, and have these people stopped to ask why and about the nature of things, about what they believe about science? No. So, wrong. So, Rogers, Priestley, good books about how science works, but no, they don't know. Okay, sorry, let me rephrase that. I think being tired, I didn't say that right. So, they are good books about the physics and give a good historical report of how things developed. Yes, 100%. But what they say about scientific method, philosophy of science, kind of how science as such works, wrong. No, they are misinformed, unfortunately. But interesting article here. A lot we can get out of it, as I hope we've done. And I hope I've illustrated in some of this discussion. But yeah, good article. I recommend people read it on their own. Look up some of these books. I'll put links to Physics for the Inquiring Mind. You can get on the Internet Archive for free, or you can buy a copy. Introductory Physics is hard to find. Oh, I think it is on the Internet Archive. Yeah, if you get an account, I think you can read it, but you can't read it kind of for free. It's not, quote-unquote, always available as Physics for the Inquiring Mind is. I think Introductory Physics is available on the internet. I think you can read it for free if you register with Internet Archive. I will check and make sure, and I shall put links to them in the show description. But Hope this helps. Important things about how to teach physics, how to think about physics, how to look at physics in context of human reasoning and human life, which is what education is about. How do we prepare a child for adult life? Education is part of that. Parenting does a lot of that. Education is part of helping a child develop. So we need to look at the bigger picture of what an adult is, what they should be able to do, what the world is like. Students need to develop their ability to reason. That's an important part of being a human. It's fundamental in so much we do. We need to know how to think. People should learn as part of their education what's going on upstairs in their mind and be familiar with it and not have it be a mystery because they're doing nothing but regurgitating and forgetting or doing a bunch of word problems isolated out of nowhere. That's not good education. But I hope this helps. As I say, we get a lot out of it. So thank you for listening. And I hope you have a good day and help our society, help people in it become better human, self-sovereign, rational animals. Peace.